Thanks for the second opportunity talk. So now it's machine learning, quantum phases of matter. So now we really want to get into the quantum stuff and apply the techniques, that we have heard about in the morning and use them in the context of quantum statistical physics. It's a great time to do so. You're all avid readers of Nature Physics, and today is the last day of the month of May, where machine learning phases of matter made the cover. This is something that I should actually say. Yuna put me into an extremely hard position here, giving these lectures. The first lecture was, giving an introduction to a 70-year-old field, and the second lecture is giving a survey of a 7-month-old field of people, running and applying these techniques in quantum condensed matter physics. So so this is also where some of our own work, will feature. We have done some work done with Juan Carasilla and Roger Melko, my graduate student Peter Bröcker, and we recruited a colleague in Germany, Farka Assad, to work with us on some of the problems that will come towards the end of the talk. So here's what we want to do. So we are jumping right in. We want to use a supervised technique to identify a phase transition. So that's our idea. So let's consider some Hamiltonian, and we know that Hamiltonian, as a function of some parameter, will undergo a transition from some phase A to some phase B at a phase transition in between. So let's assume that we have this prior knowledge. And now let's put some idea to work to identify the location of that phase transition in the following way. So we know that there is these two phases, so we can go deep into these phases and can say, well, let me train my neural network over here and generate instances of phase A, couple of thousand times. This is like generating a couple of thousand images of digits or a couple of photographs of myself, and say, well, this is phase A. These are all cats, and these are all dogs, for instance. But now it's a quantum mechanical phase, a system of a quantum many-body system, or let's start easier actually some classical system. But it's a many-body system. And let's assume we have done that. So generating these instances, and classifying them at phase A and classifying them at phase B allows us to train a neural network. So exactly what we had earlier in the morning, and identify the weights and biases of that neural network. And now let's go everywhere in between and check. So in the second step, we take that trained neural network and we run through the parameter in a continuous fashion and ask, network, what do you think? Are we still in phase A or are we still phase B? And probably it will indicate the transition in the right spot. Now, this is shockingly different from what we have done in the morning. In the morning we had 10 digits, and we said, let's try to understand that there's 10 digits. Which is a discrete set of different objects. Now we are putting ourselves in a situation where there's a continuously varying parameter, and as a function of that parameter, the images slightly evolve, and we are trying to identify the most crucial transition in these images, the phase transition.
But you can continuously evolve a 7 to a 1.
Yeah, you can do that. Yeah, that's also true. Yeah. So you can morph an image, one image in another image, and you can ask, this morphed image, does it still look like a dog or is it more like a cat? And that would be exactly the analog of this thing. But the algorithms or the ideas, that we have discussed about in the morning weren't made for that. So this is, one thing to already appreciate in taking this approach. So the question is, what are the right images, of a many-body system to feed into a neural network? So let's start simple, and let's do the Ising model. So classical spins, on a square lattice, interacting in such a way that neighboring spins would like to align in the same way. And what you see here are images from a computer simulation, from a Monte Carlo simulation of that Ising model. And as time proceeds, the temperature of that simulation is decreased, and you see a transition from what was initially random configurations to a configuration where all the spins align in the same way. So in a classical version of this problem, we can just take configurations, real space configurations, and ask whether we can distinguish them between the high temperature phase, the paramagnetic phase, the low temperature phase, where you have huge domains, and around the critical temperature where you have these percolating domains. So can we train the neural network here? Say this is the high temperature phase by just sampling that phase at a fixed high temperature and generating those images, feeding them into the neural network as labeled data, and do the same thing for the low temperature phase, and then continuously vary the temperature in between and find out where the critical temperature is. So that's what Roger and Juan have done. That's what you can read in that article this month. Here's that data. So they train the neural network in that way, and then as a function of temperature, what they will see is a function that goes from one side to the other side. It goes from 0 to 1. So there's always two functions, and there's different system sizes. There's a lot of information in this plot. So if let's fix one, these opaque colors here, that's system size 10. So it means you're looking at an Ising model of system size 10 by 10. And you train it, for instance, over here and over here. You say this is the low temperature, this is the high temperature phase. And then the output for the low temperature phase is 0 here, and it's 1 here, well, the other way around. So the output for the high temperature phase is 0 here, so it's not the high temperature phase, and it's 1 over here. And the opposite direction, the low temperature phase is 1 here and 0 over here. So these two curves add up to be 1 at all temperatures. So what you see is that there is a crossing between 0 and 1, and you can ask, here's a point 1/2. Where is that point 1/2 met? That's where the network is confused. So it cannot say whether the configurations that you are giving to the network are in the high or in the low temperature phase. It assigns 50% probability to both phases. So this point of maximal confusion coincides precisely with the location of the phase transition. So this orange bar here, that's the Onsager solution of the Ising model. So that's the known transition temperature. And then you see that as you go to larger system sizes, so that's darker colors in here, you see that these curves sharpen up and become more and more step-like, exactly as they transition, and everything seems to cross around here.
And the creep up area we extract from this crossing is
so that's next slide. So next slide will be exactly that. So because this is very suggestive of that way. Before we do that, I want to take another question and then say something.
So training at 0 temperature would seem a little bit silly. So how do you choose a low temperature?
So this is precisely the point that I wanted to come to. It's a very good question. So you already realized, the high temperature phase probably looks always, the same. It's always this disordered phase. But on the low temperature side, man, things are actually different. So at 0 temperature, you're fully magnetized. At 0 plus epsilon temperature, you get these 1 or 2 spins that are pointing up, and as you go to higher low temperatures, these little defects become larger. Eventually, they will become these domain-like structures. So to that extent, it seems that basically between every other temperature point down here, you would say these are different things. And that is, in fact, that's true. So now that's exactly a point. So one point is, what do you do? So you could choose a temperature grid. So you could, choose multiple points to train. This is precisely what these two guys did. Yeah, so they said, well, let's label a couple of temperatures, as zero, as low temperature phase, and then just for symmetry reasons, they also did this for the high temperature phase. Well, that might not be necessary. Yeah. Yeah. So that might be true. Yeah. So that's one way of approaching this. Another way would be to still, go to some, intermediate low temperature. Yeah. Probably not the most extreme case. And then, just appreciating that fact, that, things here to the left and right are slightly different, means that you are somehow now confronted with a problem that you have to put in the right amount of ignorance. Yeah. So you're looking for the big change and not for the small changes. Yeah. And how do you do that? Yeah. And how do you do that in a systematic way? It's not totally obvious. Okay. So we will come back to that point. Yeah. But it's precisely, so going very far into the extremes would be very desirable, but it might be, some caveats there. Okay, so these guys, so they chose, also probably because they knew what they wanted, these temperature points in such a way that you see this transition in the right place, and as Hong asked, now let's, try to collapse that data. So here is that collapse, so you know the critical exponent, of course, of the Ising model. If you use that, you can make a data collapse of these plots, for the different system sizes. They nicely fall on top of each other, and you even can pull out the critical temperature of the infinite system, from the finite size data. So that works.
It's a little independent of the system you use to do the training on the neural net?
So that's a next slide. You're a good listeners. So this so what it was that we have done here. So this was a square lattice Ising model. And now you could do a simple instance of what's called transfer learning. So let's say I took the Ising model on the square lattice. And I did this training. I supervised. This is a low temperature phase of the Ising model. This is a high temperature phase of the Ising model. I got all this collapse. But now I go and I simulate a slightly different lattice. I go to triangular lattice. So I go to the triangular lattice, which of course has the same phase transition. Between a ferromagnet and a paramagnet. If ferromagnetic couplings.
The question is more that you're fitting, obviously you're fitting short-range correlation functions in this thing to discriminate, I presume. So the depth of the neural net could potentially define the sorts of correlation functions you're allowed to play with, and therefore could affect seemingly you.
Yeah, so that's certainly true, but the neural network that they are using here is actually most elementary. So it has one hidden layer. It's actually not rocket science. It's very, very simple. The reason that they see this extremely nice data collapse also has much to do with the fact that they very carefully chose the regions where they were training the neural network. So here's an example of the transfer learning. So you take the square lattice, you train the neural network on the square lattice, and then you apply it to the triangular lattice. So, and you get very similar looking curves, and now you see that the transition temperature is in a different place because the transition temperature is not universal. So it comes out as a different number, but it comes out as a right different number. Okay, and you can play the same trick. Now it's the same exponent. You can collapse the data. You can try to make a data analysis of the critical transition temperature, and so on. Okay, good. So so that's the principal example. That it is indeed possible, to machine learn, very simple classical phases of matter. So we should take that.
So for each temperature, you are inputting like a series of Ising equations.
Yeah. So again, the setup is that I complement the machine learning approach with another numerical technique. In this context, it's Monte Carlo. So I'm sampling my Ising model at different temperatures, very much to the little simulation that you saw in the beginning. But for every single temperature, I just have my Monte Carlo run, and I pick, I don't know, every fifth step the configuration or something. So ideally beyond the autocorrelation time, I just take snapshots of that simulation and generate the input images for my neural network. some of them I label in the beginning and say, well, this is a low temperature phase, this is a high temperature phase, and train my neural network on those. And after that has been completed, I go to all the intermediate temperatures, and again, generate these instances, and then ask the neural network for an opinion or a prediction which one of the two phases you see. And the point is, that it makes, this hard transition from one prediction to another transition, from one phase to another phase, 0 to 1, and it crosses through this 1/2 point very much at the critical temperature. And that, as we just worked out, is not God-given. So, it's not clear that this has to work. Because every single data point here, these temperatures, these configurations have to look differently because you smoothly connect, from one phase to the other, and there's smaller changes. So if you would have, this extremely versatile, super perfectly trained neural network, it would instantly say, well, these are two different things. Come on. So obviously, temperature 2 and 2.1, they cannot be considered the same thing because I can see a difference. But this is not what you want. You want to see the difference only, on the bigger scale. Now, in this particular example, you might say, well, come on, Simon. It's so simple. I could have done this. If you just, give me configurations, I can tell you, whether something is a high temperature or low temperature phase. And I might tend to agree, that, the paramagnet is very simple to see. The low temperature phase is also very simple to see. Probably, if we were to play that game, I generate these configurations. You tell me what you think the phase is. You wouldn't be totally off. Okay, so let's go to more complicated examples. So here are the more complicated examples. Those are the ones that I already showed earlier in the morning. So now we go to these phases that very much look alike to us. So that was the high temperature phase of the Ising model. The Ising lattice gauge theory. So the that construction where the Ising degree of freedom lives on the bonds of the square lattice and is constrained to have these even numbers of parallel spins per plaquette, or here per vertex in what's called the square ice ground state. So these three phases, they you have to very carefully look now that you can see the distinction. But as I'm telling you what the distinction is, in explaining these features to you, I'm making clear that all you will have to look for to distinguish, this phase from that phase from that phase is something local. So if you stare around, 4 of these guys, around a plaquette, you will be able to see whether they fulfill this constraint or none of these constraints. So that's what will allow you eventually to distinguish these things. So I see some of you staring and trying to do this live. So that's interesting because it will distinguish a paramagnet from the Coulomb phase in the square ice model from what's called a loop gas in the Ising lattice gauge theory. So that's interesting because all of these phases don't have a local order parameter. So the loop gas has something non-local. You can talk about winding of loops. The Coulomb phase has a divergence-free condition that you can impose or that is imposed, and that you can see. So distinguishing these things is far less trivial. But again, you can do this to a similar quality as in the Ising model we have just seen. So distinguishing these features. So now here's no phase transition that you can drive immediately between these 3 different phases, but it's reassuring that you're able to distinguish them with this technology. Good. So that's sort of the warm-up. So now let's go to a quantum phase. So a quantum system, and try to pull off the same story. So here's our favorite version. So I'm like Hong. I like fermions. So we look at fermions living on the honeycomb lattice. So and we take a very simple Hamiltonian. We have some kinetic energy, some hopping energy. We have some repulsive term, and that will have the system go as a function of u over t, go between a semi-metal and a spin density wave phase. So the semi-metal is the one with the Dirac cone, and this transition is, as Hong explained, it's a special transition because in addition to your order parameter fluctuations, you have the gapless fermionic modes. So this type of phase transition is different from the transition that you have in any bosonic system. So it's a fermionic, a genuinely fermionic type of transition, so it's a Grosne-Will type transition. It's something that we also know very well in this particular case because it's very much of a toy model. Okay, so here's a browser. Yeah, so let's strip away the spin degree of freedom and look at spinless fermions, and I can drive a very similar transition between a semi-metal and a charged density wave in that model if I have a repulsion between nearest neighbors. Aha. The distinction, and that's going to be an interesting one, is that this first example has no sign problem. Yeah? So that means I'm good to go and write a quantum Monte Carlo code and work with this problem. Now in the second version, if I work with complex fermions, I will have a severe sign problem. Yeah? So that means that I have some problem in my Monte Carlo, and we will talk about this. I can overcome that problem by listening to Hong's lecture tomorrow, yeah, and change my basis and go elsewhere and not have that problem. So for us, a perfect test case. You can turn on and off, this problem, yeah, and see, what it will do to us, and that will be part of the story that we will be interested in. But let's forget that for a moment, and just think, okay, now we have some quantum system, spinful fermions on some lattice, undergoes a phase transition, still as a function of a single parameter. So we can apply, the same idea. Yeah, we train, deep in these two phases, the semi-metal and the spin density wave phase, and we try to identify now this Grosne-Will transition by applying the trained neural network to instances in between. But here now, of course, the question is, what are the right images here? Yeah, to look at, to represent that quantum state. Yeah, so so we want to use images because images were the key ingredient in these image recognition algorithms that have become so powerful. So that's what we want to work upon. Good. So so we have to go somehow now into technicalities and understand what we do when we simulate these systems. So before we do so, we answer a question.
So it seems like we had some other questions about this also. It seems like you need some representative states for each phase, and you need to know where they are roughly. So if you have something that's not just a single transition point, but there's 3 phases as you change the parameter, then it seems like finding something to train for the middle phase would be really, you need to know something from the method or
see, we're all the same, yeah. So so that bothers me too, and there will be an answer to that later on. Okay, so we go one step after another. Yeah. So now our knowledge is we somehow know that there is 2 phases and only 1 transition. Of course, we want to answer, what happens if there is 3, and you will see an example of that, okay? So it's going to be all good. Okay, so very quickly, so we do Monte Carlo, and we do this for fermions, not probably the standard Monte Carlo flavor that most of you have somehow heard about, which is typically world-line Monte Carlo, Feynman's idea of going into an extra space dimension. This is not what we do here. In auxiliary field or determinantal Monte Carlo, what you introduce is the auxiliary field, and you do so by making a Hubbard-Stratonovich decoupling, a Hubbard-Stratonovich transformation that allows you to decouple these quadratic direction terms and gives you free fermions, moving in a background field. And for that background field, you have to, calculate these determinants. Yeah. Okay. And effectively, what you do is you sample, that auxiliary field, and that's very much like a classical problem. And because it's very much like a classical problem, that was also our first shot. We said, Roger, the Isaac model, that looks like our auxiliary field. Yeah. We just have to take that auxiliary field and work with that. Yeah. So here it is. Yeah. So I start with my fermionic degree of freedom initially on the side. Yeah. After that Hubbard-Stratonovich decoupling, what I add per site is this auxiliary field. And now if I have a lattice model, we're in real space, and I have all these different degrees of freedom. Each of them acquires this auxiliary field. If I now go into projection time, I do 0 temperature Monte Carlo, and there's a projection into the ground state, gives me a second dimension. Yeah, every real degree of freedom comes as an auxiliary field. I only consider the auxiliary field, can be up or down, gives me an image, looks like the Ising model. Yeah, so I say, oh great, yeah, so here's my image, yeah, let me use that in this machine learning approach. So now you actually already get a gist of, what is actually that you are trying to do. Yeah, so you're looking for the right information to feed into your neural network. Yeah, so for us, it's the search for the right image. So here is our shot at it. Yeah, so here are pictures of those. Yeah, so for the Spinful fermion case, we do this Hubbard-Stratonovich decoupling. We can do this in different ways. Yeah, we can couple it to the backalization, which will break the SU2 symmetry of the system. And then you see that the semi-metal, typical auxiliary field configuration looks like this, and the spin density wave looks like that. And you will probably say, oh, that's nice. They look different. Yeah. If I do a charge decoupling and preserve SU2 symmetry, despite the different color code, there's also a distinction that the semi-metal and the spin density wave very much look alike, at least to my eyes. And now let's check, what we can do with the neural network on these types of configurations.
So after Hubbard-Stratonovich transformation, do we still have a sign problem?
So in this particular case of Spinful fermions, I have never a sign problem. Yeah, and the sign problem arises after the Hubbard-Stratonovich. Yeah, so what I said, I sample the auxiliary field, and then I have to calculate the determinant. The determinant will come with a sign. It can be either plus or minus 1. And if that sign starts to be either plus or minus 1, that will induce the sign problem. We will hear what that is in a second, okay? Yeah. So then the question is, what do you do? Yeah. But right now we don't have that problem, okay? We are still in the safe world of no sign problem, and all the determinants are plus 1. Yeah. So we can generate these instances, and we are just asking at this point, what is the right image? Okay. So we are just asking, whether the auxiliary field, will allow us to make, pull off that same trick as in the Ising model.
So this is only true for the half field, right?
Yes. Yes. We also have, we've gone away from half filling too in these things. And then if you go away from half filling, you have a sign problem. Yeah. In the Spinful case. Yeah. And then Hong's trick doesn't work. Yeah, so, but now we're getting ahead of ourselves. Yeah, let me show you a picture. So, we were, at this point, we might have rushed to a conclusion. We would have said, the charge decoupling, man, this looks much alike. Let's take the magnetization and we will be fine. Okay, so here's our plot. Yeah, so we crank up the interaction. Yeah, and now these things are shifted vertically. I go from this types of configuration to these types of configurations, and indeed, somehow my prediction of the neural network, trained here, saying, this is the one phase, and trained over here saying this is the other phase. It is able to distinguish these two things, yeah? So it comes out as 0 here, well, 10 to the minus 12, and it comes out as 1, 10 to the 0 over here. So it does have this, 0 to 1 thing, but then, it goes up, yeah? So the critical value of the transition that's here, and that has nothing to do with, this value being 1/2. That would be somewhere here, yeah? So that doesn't work. Yeah, it gets even worse if you do this. Yeah, so if you do the charge decoupling, you train, and after the training, nothing got understood. Yeah, so you generate instances of this phase, and you ask, did you learn it? And they said, well, 50%. Which, okay, so nothing. Yeah, and it's solidly 50%. Okay, okay, so this doesn't work. Yeah, so the auxiliary field, our initial guess. Yeah, what you could use didn't do the trick. So we looked for something else. Yeah. So I said, well, probably we should use a more physical observable, like this equal time Green's function. Yeah, let's do that. So now the aficionados will say, well, you don't have to go there at all, yeah, because I know if you have a Hubbard-Stratonovich field decoupling and you have the auxiliary field, you can just calculate the Green's function from it. So if the auxiliary field didn't work, this will not work at all neither. That would be, if you would assume that, the neural network, the stuff that I've shown you, is super capable, and the first thing it does in the first layer is like, let me take this auxiliary field and calculate the Green's function from it. I can tell you, my experience from the last month is it's not going to what's happening in the neural network, okay? So that's why we have to do this, yeah? So we use a Green's function, okay? So we calculate from the auxiliary field, our pre-processing step is calculate the Green's function. yeah, equal time single particle Green's function, yeah, and we have to look at it, yeah. So now the Green's function is a complex valued matrix. So in order for you to see something, yeah, I have to you know, work, you know, and make a complex number for you visible. What we will be using for your pleasure, not for the neural network, that doesn't care about the complex number, is this HSV scheme, you know, hue saturation value that you know from your computer. So you take a complex number and you know, you take its amplitude and phase, and then you do something slightly counterintuitive. In this picture, you take the amplitude, and that is the hue. So that is where you are on this circle, and the saturation, the phase, is you know how much you go in, and the opacity we are not using. Okay, good. So that allows me to show you the Green's function. So here it is. Yeah. So in the semi-metal, it looks like this, and in the spin density wave, it looks like that. Yeah. Okay. So you see, this is reddish. This is more greenish. Aha. So there's a distinction. You see, there's you know an element here on the diagram. Well, yeah. Okay. So probably it's not. Yeah. So you might see a difference. Yeah. Our network sees a big difference. Yeah. So this is where this approach works. Yeah. So we can go in and we take, you know, these red dots, mark, you know, the single parameter at which we generate these images, and tell the network, this is a semi-metal, this is the spin density wave, and then we go everywhere in between and even further out into the phases, yeah, and ask, you know, where do you think, you know, these Green's functions belong to, yeah, and now you see this curve which goes from 0 to 1. And it goes to 1/2, you know, the point of maximal confusion, you know, here, and that point is between, you know, this solid line and this dashed line. The dashed line is, you know, the Monte Carlo estimate, you know, that you would obtain by using exactly the same type of system sizes, and you know, locate the transition. You know, you would put it here, yeah, and then if you go to the K computer, the world's largest computer, and you know, calculate a couple of extra system sizes, yeah, you would come to the conclusion, whoops, it's over here, yeah. So this is a transition with tremendous finite size effects. Yeah, somehow we end up, you know, here in the middle. Yeah, not that I give much about that. Yeah, the point is, you know, we see the transition and we see it in the right spot. Yeah, so certainly this is very different from, you know, the Ising model data. You know, where you had seen data that, you know, got us, you know, the Onsager solution, you know, to 2 digits, yeah. So here we are not in this 2-digit regime, but we're also doing something different, yeah. So here we do really this approach where we only take 2 points, yeah, and train and not, you know, a gazillion points. So here that question is still valid, you know, why does it work, yeah. So here it seems to work because, you know, the Green's function apparently do not, you know, change dramatically as I vary, you know, this parameter within the phase, yeah. So it's not like the Ising model where we know that this, you know, stuff changes quite a bit actually as you vary these parameters. Okay, cool. So some intermediate conclusions. So we learned that quantum Monte Carlo and machine learning, like Monte Carlo, classical Monte Carlo machine learning, can be used to distinguish phases of interacting many fermion systems. So that's already something. Yeah. So for us, you know, Green's functions are the ideal images for machine learning. That is something that we learned on the way. And apparently, you know, this ensemble of sampled Green's function contains sufficient information to discriminate these phases. Yeah, so we haven't given any further information, but you know, these Green's function to the neural network. Good. So that's encouraging that we can put ourselves out of business by, you know, having neural networks, you know, calculate phase diagrams for us in the future. But let's go, you know, to where the meat is, and that's where the sign problem is. Oh.
So how about computing the spin-spin correlation?
Mm-hmm.
Instead of calculate the structure back, just with the vector.
Yeah. So
Instead of single.
Yeah. So now comes a question of taste. So between, you know, so what Hong is asking, so why did you take the Green's function? Why didn't you take something that is more discriminating between the two phases and have learned on that? Yeah. So our idea in doing this was to not do that. Yeah. So as a matter of choice. So we wanted, you know, to work ourselves towards an algorithmic toolbox that will allow us to, you know, look at phase diagrams of models without prior knowledge about, you know, order parameters and these things. So we were looking for something generic, yeah. in that extent, you know, the Ising model configurations were not generic, yeah, because the Ising model configurations are, you know, a direct image of the order parameter basically, yeah. You know, the order parameter is the magnetization in the Ising model, so you can just count the number of up spins and you're done, yeah. So at that sense, you know, the Ising model configurations are very simple, yeah. So they're almost presenting the perfect information for the model, while we are looking for something generic. So I realized I have to speed up. I don't have 2 hours because the last speaker just arrived. So let's go where the meat is, and let's do the sign problem. So I will rush through this because you will hear this at least one more time tomorrow from Hong, I guess, who will give his perspective on, you know, what the sign problem in Monte Carlo simulations is. Let's remind ourselves what Monte Carlo is. You know, Monte Carlo is this miracle technique, yeah, that guides us through a high-dimensional configuration space. You know, even for the classical Ising model, you know, configuration space grows exponentially. It's 2 to the n, yeah, and still, by generating this Markov chain, we can go through that exponential space in polynomial time and calculate expectation values of observables. That's what we can do in polynomial time. And the way it works is, you know, that we have, you know, these transition probabilities between configurations in this Markov chain that use, you know, the ratio of probabilities, in this case, you know, the canonical ensemble of Boltzmann weights of the classical problem. And, you know, going from this exponential scaling to polynomial had tremendous impact. You know, Monte Carlo has, you know, worked through many fields, you know, and made them, you know, basically computable. If you go from classical to quantum Monte Carlo, yeah, when you go from the calculation of the expectation value of some observable from just summing up, you know, configurations in your Markov chain and calculating, you know, the observable on the fly to quantum, you have to go, you know, to trace. Yeah? And the way that this is done in quantum Monte Carlo is that you map, you know, your quantum to a classical system. Yeah? So this can be in terms of world lines, yeah, where you know, generate an extra dimension, you know, the imaginary time direction, and your classical configuration that you look at, you know, are these world lines. You know, so you play with these spaghettis, yeah, and every world line configuration is a classical configuration, and you sample those. And again, you know, you can, you know, calculate expectation values in a polynomial time, or alternatively, in the fermionic flavor of Monte Carlo, you don't do world lines, but you're dealing with this auxiliary field, and that is classical, and that allows you to do the same thing, but you have to calculate these determinants. Good. Everything is fine up to the point when you realize, you know, that, you know, these probabilities here, yeah, for the configuration that you're working with, you know, world line configuration or you know, your auxiliary field configurations, in the quantum problem, when you calculate the probability, they might become negative. That's not yet the sign problem, okay? They might become negative. So what you say is, well, let me ignore the sign. Yeah? So I say, well, if p becomes negative, I don't care. Let's just work, you know, with the absolute value of p. Yeah? So if there is a minus sign, I just strip it off. So I can just write, you know, this guy, you know, this expectation value in this way. So instead of, you know, working with, you know, the original weights, I work now with the ensemble where I mod, you know, all the probabilities and pull out explicitly, you know, a prefactor, which is the sign. Yeah? So the expectation value of this observable becomes the expectation value of the observable times the sign in an ensemble where I take the absolute value of the probability and I have to divide by the expectation value of the sign in that modified ensemble. That is a correct statement. Yeah? So going from here from the left to the right, nothing has happened. So no problem whatsoever so far. Okay? I'm still, you know, able to calculate this expectation value. But the but is, yeah, that, you know, this average sign here in the denominator, that decreases exponentially. Yeah? So that's not good. Yeah? So that's this guy here, yeah, goes to 0, like the exponential of the minus the inverse temperature, the system size, and the difference in free energy densities between the ensemble that you have, you know, that you wanted to simulate, yeah, with the positive and negative signs, and the one where you only take positive signs. Yeah? So that's this difference here. And but not good is that the lower the temperature and the larger the system, the faster you go to 0. And not only does the denominator go to 0, but also the numerator. So you're dividing 0 by 0, yeah, and that's not good, yeah. So if you divide 0 by 0, you get arbitrary numbers. That means that the statistical error associated with this expectation value, that actually grows exponentially. That is a sign problem. Yeah? The sign problem is you go from this expectation value to that expectation value, and calculating that expectation value, doing everything correctly, yeah, you realize that your statistical analysis screws up and gives you this exponentially growing statistical error. That's a problem because the entire beauty of Monte Carlo was go from exponential scaling of Hilbert spaces to polynomial. But now you're back to exponential, and exponential means small system sizes, everything sucks. Yeah? So that's a fundamental limit of Monte Carlo simulations in the simulation of fermions, where this negative sign makes its way easily into it. Yeah, the many electron system. Yeah, so why can't we discuss phase transitions in metals? The emergence of superconductivity and these kind of things very easily. Well, because of the sign problem. Yeah, the field of magnetism has been killed by Monte Carlo simulations, but the field of frustrated quantum magnetism and spin liquids, where the sign problem enters. Yeah, so these are the types of problems that you cannot just numerically simulate and get every number you ever wanted. So these are the open problems. Good. So it's a very fundamental problem. Yeah, but it doesn't have to be there. Yeah, because the sign problem is a basis-dependent problem. Yeah, so if I were to go from my simulation basis to the energy eigenbasis, sign problem will be gone. Yeah, because in the eigenbasis of the system, there will never be a negative probability for anything. Oh, good. So I just have to go there. But that would be the same as diagonalizing my Hamiltonian. That's what we know from diagonalizing things. That's exponentially hard because of the large Hilbert space. So that's not an option, but it shows us a glimpse of hope. It shows us that probably your simulation basis was just poorly chosen. And what you should have done is, you should find a basis change to some other basis, probably not the eigenbasis, that will do the job. So this happens every now and then. Yeah. So in the heydays of superconductivity, Kai Wiese, found the Meron cluster update, which was a sign problem-free approach to the Hubbard model. Unfortunately, not where we are most interested in. Then many years later, Chandrasekhan, who has been devoting his life to the sign problem, came up with something called the fermion-Beck transition method. Tomorrow, you will hear from Hong Yao. Well, really, what you should have done is, you should have gone to Majorana fermions. That will allow you to, look at a couple of interesting problems, and it's something that we will make use of in just a few seconds as well. So Hong will talk about this tomorrow. Yeah, but what you should realize is that hope is, these things are happening not very often. Yeah, so it's very hard to identify a basis condition. So there's a very influential paper from 2005, and that says, well, if you don't, want to rely on the genius of smart people, but you want to automate that task. You want to have a computer find the right basis. You're not going to be successful. Yeah, so there's no general solution to this basis change problem. Yeah, so identifying the right basis, that's an NP-hard problem. That doesn't mean that the sign problem is NP-hard. Yeah, so that's what I'm teaching you right now. Yeah, it only means that one particular solution to the sign problem, identifying the correct basis, is NP-hard. Yeah, it doesn't mean that Hong is not able to find a cool basis. Yeah, it only means that he's not able to do this generically for every problem. Yeah, because otherwise he would have solved an NP-hard problem. It doesn't mean at all, that there is no solution to the sign problem. So other things that are interesting is, you can go and change your perspective. Yeah, so you say basis change is not my problem. That I want to, my perspectives that I want to take on the sign problem. Let me go around it. Yeah, let me be very clever. Like Eresberg, Max Beditsky, and Subir, who for exactly the type of problem that Hong was discussing earlier in the morning or the afternoon. The problem with the Fermi surface, these fermionic phase transitions. You sometimes can write free actions that are sign problem free. probably he will talk about this tomorrow as well. We had our own shot at this, thinking about entanglement entropies and thinking how the sign problem enters, in their calculation in a different way than here. So now let's add, these two together, okay? So and see how that works. So the idea is, to get rid of this step, So this step, that's the statistical analysis, of the situation where you ignore the sign introduces a problem, that you go from here to here, and then you divide 0 by 0. Let's not do that, Let's just not do that, So let's just ignore the sign, and ask, whether our machine learning stuff, can identify a function, that will just do the trick, It will be 0 in the one phase, and it will be 1 in the other phase, and it will allow me to go around the sign problem, by identifying exactly such a transition. So how does it work? We simulate a modified ensemble where we ignore the sign of the weights, and in that ensemble we apply the machine learning approach. Okay, let's do that. Here's a final thing. Okay, so here's a result. So these are now the spinless fermions. Spinless fermions, in our basis, without using Hong's trick, has a sign problem. It's a very severe sign problem. The sign is 0. It's everywhere 0 here. Okay. Still, we go in and say, well, let's take two extremal points here, and at these extremal points, tell the neural network what you are sampling are two different phases. So what you see here, is the one phase. What you see over there is the other phase. And now let me go everywhere in between and ask, what you think, we are sampling. And then you see that again, we get this transition. So there is, the distinction, that initially worked. Will soften up, and there will be a point of confusion, and this point of confusion will, as you increase the system size, move, and it moves toward this point. This line here is the known exact result. It's the known exact result because Hong can use a trick, go to a different basis. In that different basis, he doesn't have a sign problem. He can just solve the problem. So he kills it. By doing regular Monte Carlo, and he tells me, Simon, here's a transition. And I say, oh, that's nice because it seems to be close to where all this data goes to. So that's extremely interesting. So let's say it like that. So have we done a miracle? No. So we haven't solved the sign problem. We have shown in this particular instance that we can somehow work our way around the sign problem. Using this machine learning approach. Have we solved an NP-hard problem? No. The NP-hard problem was, this basis changed. And we didn't do a basis change. We did a different thing. We just asked, whether the neural network is able to make the distinction between these two phases and see a transition, and it did. Okay.
It's still computing discrete function.
Yeah. So it's still calculating the discrete function. So now someone might say, well, I still don't believe a single word, because you're applying a level of ignorance, and you're ignoring the sign, and that that you shouldn't do this. I have heard that ignoring the sign means you go from a fermion to a boson problem. You go from an antiferromagnet to a ferromagnet. You go from something extremely interesting to something extremely boring, and why the heck can you see still a transition at the right place? So all these statements that I just made are true for world-line Monte Carlo, where ignoring the sign means that you are sampling a Hamiltonian with flipped overall sign. So it's something dramatically different. You go from an antiferromagnet with some spin liquid ground state to a ferromagnet which has a polarized ground state. And you cannot expect the two things to be the same. Here what we do is slightly more subtle. When we ignore the sign of the determinant, what we really just ignore is the number of fermionic windings, the parity of that number. It's a level of ignorance on a different level. So it raises the question, which kind of phases distinguish themselves by whether they have an odd or an even number of windings of the fermions, and those we will not be able to distinguish. But if that is not a matter, then you're apparently fine in the sense that you can make a useful statement. Anyway. So let's leave it as an interesting observation. For us, it's not a controlled thing. So we cannot tell you whether by applying this to one problem, it will also work on another problem. For those problems that we looked at, we're hopeful. Yeah, and it opens a window of opportunity. Okay, so someone asked about 3 transitions. Let's go and go from supervised learning to unsupervised learning. Up to here, we used some prior knowledge. We said, well, there is 2 phases, a phase A and a phase B. I use labels, and I say, here's a phase A, here's a phase B. Let me identify the transition. Let me get rid of that. So let me not label anything anymore. And try to identify phases. So this is work that I've done with my student and Faka, and related ideas, from Evert and Sebastian. They call this learning by confusion. It's a different approach, but it has the same touch to it, that you go from a supervised approach and make it unsupervised. This is what we want to do. Here's what we do. We go to something simpler. So no longer fermions. Let's do bosons. Let's do hardcore bosons on a square lattice, or equivalently an XXZ model. And as a function of parameters, it has a very well-established phase diagram. Which you know for many years. The interesting point here is, it has a superfluid phase. It has mod insulating foils of different densities, and there's even a checkerboard solid. Okay, so there's now 4 different phases. Okay, and now let's do the following. Instead of making this extreme approach where I say let's go deep into these phases and train a neural network, let's do something different. Let's take a window, a small window, and let's pretend, that these 2 points, that we are distinguishing on the left and the right are different phases. So we sample, on the one point, and we sample on the other point, and we tell the network this is phase A and this is phase B, independent of whether they're actually 2 different phases. We just do that, and then we take that window and we shift it around in this phase diagram. Now, in all the curves that you have seen so far, where this worked, you've seen that they go between 0 and 1. Which meant that a priori, when I said this and that point, the first information that we received from the neural network, it was actually able to distinguish the 2. It was able to train itself in a way that it was assigned consistently 0 to the one phase and 1 to the other phase. So it saw that there are 2 different phases. So let's move these 2 extremal points very close to each other. That also gets rid of your problem. The fact that maybe something is changing on small scales. Well, now we are on the small scale. Okay, so now we are just asking, do we see a difference between these 2 things? And now let's move this through. Okay, so here's the answer. So we look again at the single particle Green's function, which is this SE correlator here. Well, it says preliminary results, but you can see the phase diagram. Okay, so we scan through this like here. And what you now see is basically the differential of the curve that we have seen before. When I get 1/2 and 1/2, so the neural network is not able, to distinguish, that these 2 points here are in a different phase. It's blue. It's color-coded, And if it's above 1/2, it will, gradually go into yellow, and you nicely see that phase diagram. Okay. Okay. So there's 1, 2, 3, 4 phases, very different phases, and you can see those. So now it's a question of, of size. So the window, so it's slightly bigger than this, so it's very small. Okay.
And when you say whether you can distinguish or not, is that about whether you can successfully train?
So that's all we do, So all we do is, so we only train, So we take these 2 points. We take, we Monte Carlo sample in the background. We say, here's 1,000 instances of that point. Here's 1,000 instances of that point. We tell you these are 2 different ones. And do I now succeed in seeing that? We have seen before instances where we, took that and it didn't work, and we got this 1/2. So this failure is everywhere here. We can go to the to the off-diagonal correlation function, and that is not as nicely. Yes. But we also you understand also why that is. So why some of these phases are in which of the 2 correlators look better than the other ones. Okay. So.
With the Ising configuration?
What's that? Yeah, so the other one, oops, it doesn't come.
Did you learn with the Ising configuration?
Yeah, so what?
Here, did you learn?
Yeah. So that's so that's why it's so much simpler here. Yeah, good. Now we got Faka Assad on board because he has a cool model. So he has fermions coupled to a quantum Ising degree of freedom on the bonds of a square lattice. So it's something that Faka and Tarun looked at, and at the time Berkeley group around Sneer and Ashwin. So this model as a function, so here you have fermion hopping, they're coupled to the Ising degree of freedom on this bond, and now you put in a transverse field. As you put in a transverse field, you will drive a transition from a topological to a non-topological phase. Aha. Yeah. So let's see whether I can see that transition. Yeah. So it goes from a Z2 Dirac phase to a spin density phase. As a function of this magnetic field here. Here are Green's function images. Yeah. So they look well. So these are all sampled in this phase at the same point. These are sampled somewhere here. Yeah. They look alike. Yeah. But in both approaches, both the supervised approach where you tell them explicitly. Yeah. So here and here, there's two different phases. You see a transition, and in this unsupervised approach where you shift the window, you see consistently 1/2, and then you spike, and this point of 1.6 is at least as good as I got originally in the Monte Carlo data, doing pure Monte Carlo and trying to see the transition. So that's actually very nice. So here we managed to see the transition between a topological and a non-topological phase without pre-processing. Yeah, so we didn't have to do what Una and Frank have devised. The reason is that in this case, the elementary topological excitation, the Y-zone, is actually encoded in the auxiliary field. So in the it's a point-like object in the auxiliary field, and as such also has its remnants in the Green's function. So it's in that sense a simpler version probably of a topological to non-topological transition, and you can see it with simpler approaches. But it's still cool. Yeah, you can do this, and you can even do this without a priori knowledge. Good. So let me close in the last 2 minutes, reviewing for your benefit very nice work that Giuseppe Caleo has done on quantum state tomography. Yeah, that's how they call this. Work together with Matthias at ETH, where they use reinforcement learning. Remember, in the morning we had this Atari game of, this brick wall game. That was reinforcement learning. Let's do reinforcement learning on a quantum wave function. So what they use is called a restricted Boltzmann machine. That's a mini neural network of this sort. We have a visible layer of physical degrees of freedom, and you have a hidden layer of additional neurons. And they are connected in this, everyone by everyone network. And the one thing that you adjust yourself, to allow is, the number of hidden layers here. So there will be a parameter that's called alpha, that counts how many more hidden variables do you actually have compared to the physical variables. And we will play with that. Yeah. So now I take a wave function, which, as a function of my physical variables, and the neural network, all these weights in here, I can write in this way, So, I write it in this way. So it has a bunch of variational parameters which depend on the physical spins, some prefactor on the hidden guys, and the coupled version of the two. Okay. Good. And now I train, in a reinforcement step, these variational parameters. So I sample the wave function with the current set of these parameters. I get a feedback from some variational principle. So like the energy. Change the network of parameters and go through this. So that's my scoring function. The variational principle. And in doing this, I can create variational energies. So as a function here of the iteration, which means as a function of training steps, you see here for the 1D Heisenberg model, the variational energy that's coming out of the network. That's these curves. The exact solution is, the exact known number is down here. And now this alpha parameter was, as many hidden variables as visible variables, twice as many hidden variables, fourth as many hidden variables. And you see that, oops, they all nicely converge, to the exact value. But you see that, having more of them, brings you to insane precision, close to the exact value. Even cooler is this. So now we look at a couple of different models, the 1D transverse field Ising model, the 1D Heisenberg model, the 2D Heisenberg model. Now as a function of, this parameter counting the hidden numbers of variables, and you look at these variational energies, and so the really nice examples are here. The 1D Heisenberg model, you compare to your best variational Jastrow approach, and you're consistently below that. Being below that means you're the winner in this game, okay? Because you found a variational energy that is lower, so apparently you managed to write down a better wave function than those guys. Okay, so you say, well, Jastrow probably that's, let's do something more sophisticated. You go to the 2D Heisenberg model, and we use, for instance, PEPS, which up to this paper was, the best variational energy for that model, and you see, you easily fly below that energy. Okay, it's all on super mini scales. But what it shows you is that you're able to come up with a variational approach now that blows out of the water. These super sophisticated actually techniques. PEPS is something that is very hard to program. We heard this in the context of Mera earlier in the day. So it requires a lot of algorithmic power and implementation power to do this right and then come up with these lowest bounds. I can tell you this machine learning approach didn't use any of that, okay? So that was, quickly done and, has beaten those guys. So it's it's the same guys, Matthias is on both sides of these lines, but it's still incredibly interesting, okay? So we get very high precision, in these reinforcement learned Boltzmann machines. We have an extremely compact representation, compared to the matrix product state, that is underlying, for instance, PEPS. So the number of parameters is 2 orders of magnitude smaller. Still you do better. Over these systems. So that's another avenue where you see that's going to be interesting. Okay. So let me close and let me say the following. So what we have seen by example is that Monte Carlo and machine learning approaches can be used in combination to distinguish phases of interacting quantum many-body systems. So strongly correlated systems. You have seen it opens an opportunity to think about the sign problem in a new context. This is just the beginning. So all of these results have been created within the last 9 months. Probably what we will see in the future is much more of this. What would be interesting is the analytical side of things. What I haven't talked about at all is connections between neural networks and matrix product states that have been emerging. Connections between deep neural networks with multiple layers and the renormalization group. A topic dear here in Cornell. There's 2 sides of that story already. So there is a connection between deep neural networks and the renormalization group. No, there's not. So let's see how this works out. The connection to matrix product set is very interesting. Because we know a lot about matrix product state entanglement and representations of states in these matrix product states. So this is just the beginning, and probably the future will bring us an interplay between machine learning, and quantum statistical physics in a similar way that we have seen in the last 10 years between quantum statistical physics and quantum information, where these 2 fields have been interplaying and benefiting from each other in a big time. So probably the same thing will happen here. We have, or I have discussed, taking machine learning approaches into statistical physics, but probably it's also good to go from statistical physics to machine learning to actually explain how their algorithms really work. Something that after 70 years of development, they haven't cared about too much, but probably we do care. And probably we have the right language. So that's what we can bring to the table. So your solid education might be good to explain why some of these machine learning approaches actually work, how they work, and that would be cool for all of us. Okay, and with that, let me close.